Good morning, everyone. I am happy to give you a presentation on the remote detection of marine plastic litter, which is quite a new topic and actually received a boost about the last years. I think it's also a quite relevant topic for this community. So I think you all know the problem of marine plastics. This gives a little bit of an overview of the problem, which is actually coming from a publication from Le Breton in 2019. So you have the larger macroplastics and the microplastics, which are often coming from the macroplastics. And these two figures shows what happens if we keep the emissions at the level of 2020, or if we fully stop the emissions in 2020. If we fully stop the emissions in 2020, you can see at the left that the macroplastics in the ocean surface layer will decrease. But even if we fully stop the emissions in 2020, the smaller secondary microplastics will even further increase, at least until 2050. So our goal is to focus on these macroplastics, so the plastics larger than about 5 centimeters. Because actually very little information is available on the distribution and quantities of these plastics. But a very large volume is associated with these macroplastics. Then they also decay into microplastics, which are quite hard to remove from the ocean then. Also, they are very much undersampled by the current measurement techniques, such as the plankton nets and the sightings. They are much rarer, so they are sometimes just not collected. Our focus is also on the detection, the removal of these plastics in rivers, ports, and coastal areas, and prevent them actually to enter the ocean, where they are much harder to detect and to. We have a background in ocean optics, so we wanted to better understand the spectral reflectance of these marine plastics, and for that reason we set up a tank construction at Flanders Hydraulics. So in the figure A here you can see the original tank, and we developed a construction on top of this tank to be able to attach lights, but also attach our ASD spectrometer and also a holder for the plastics. And we were then able to lower the holder and submerge the plastics into the water of the tank. There is also a kind of a steering wheel which allows us to add sediments and suspension. The results of these experiments, they are already published in 2 scientific publications, which you see here at the left. And also the database is available at 40U as in open access. So we tested a lot of different plastics as plastic bottles in different degrees, different, for instance, crushed, non-crushed. Also placemats in different colors, ropes in different colors, and also real weathered samples, which we have collected in the port of Antwerp. This is a first example. This shows the spectral reflectance of the weathered samples from the port of Antwerp. And actually we knew already from industrial sorting that the plastics have specific absorption features in the shortwave infrared. And we also saw this in our spectral reflectance measurements. So for instance, around 1215, you see an absorption features at 1660, at 1730, and so on. In the visible, we do not have a specific plastic reflectance, and the reflectance here is very much linked to the apparent color of the plastic. Of course, we need to realize that when the plastics are slightly wet or when they are submerged, you have the very strong pure water absorption, which will totally change the reflectance of your plastic. And this is a nice example of an orange placemat, which we measured in the tank. You can see the reflectance of the dry orange placemat in the blue. And what happens if it's wetted in gray? You can see that the reflectance decreases, but you can still see the reflectance in the shortwave infrared. But if we submerge the plastics about 2.5 centimeters below the surface, you almost don't see anything anymore in the shortwave infrared. You only see like a small feature here around 1070 nanometer, which is due to a local decrease in the pure water absorption coefficient. A similar experiment with different suspended sediment concentrations. This is for a sediment concentrations of 75 milligrams per liter, and this one of 321 milligrams per liter. And you can see how this actually changes the reflectance especially in the visible. Also, what we need to think about is how the shape, the appearance of the plastic change the reflectance. For this, for instance, this is a rope on a roll, unrolled and also aligned along a frame. And you can see how the state of this rope gives a much different absolute reflectance, mainly in the shortwave infrared. Further, if we want to go outside and try to detect plastics, we also need to consider how we can differentiate between the plastic reflectance and surface features, such as white cap, but also the water itself. And this is a very nice example. We, for instance, see the reflectance of a plastic bag in green. And you can see the reflectance it's actually a modeled reflectance of white caps in the black dotted line. You can see how similar they are. Also, you have the spectrum of a submerged orange placemat in light orange, and a spectrum that we measured in the Scheldt River of turbid water in blue. And also there you can see how much they are really alike. So this, you can see here, it's not always so easy. It will not be easy to detect the plastics in the real environment, and we might also need different solutions, different algorithms, depending on the type. Based on this experience, we did try to specify the spectral bands that we might want to have for detecting marine plastics. And as you can see here, it's a combination of visible, near infrared, and also shortwave infrared bands. Based on this table, we also set up a collaboration with the camera manufacturer to develop a specific marine plastic sensor, which has most of the wavelengths here. Although we don't have the longer wavelengths beyond 1700, because that's at the limits of the in-gas camera that was being used by the manufacturer. We do think if in case we have very high spatial resolution data sets, such as coming from a drone or from a fixed camera, for instance, on a bridge, we do think it would be better if we can combine the spectral information also with some AI, which takes into account the shape of the plastics. This can, for instance, be beneficial if you want to discriminate like this plastic bag from a white cap and so on. And we started this in 2 new projects. We did some first tests with a drone on the lake nearby our offices, where we put a lot of different bottles and bags in the water and set up a first AI model to be able to detect plastic bottles, which worked actually pretty well. And we now want to expand this to a larger variety of plastics. We have some new data sets taken in Belgium, but also in Vietnam. We will be also collecting data sets obtained from bridges. We will be putting cameras on bridges in the port of Antwerp, but also in the port of Ostend and the Scheldt River. So yeah, what we have learned so far from these experiments. So our goal was to better understand the spectral reflectance of marine plastics. It's not so easy because you have a lot of different variables you need to take into account. You have the color of the plastics, you have different polymer types, there are coatings, you have different shapes, they can be wet, they can be submerged, so you really need to do this in a quite a controlled way. If you would immediately go outdoor and measure the plastics in an outdoor environment, it's very difficult to understand what you're exactly measuring. So sometimes you might think it's like a different plastic material, but in the end, it's the same one, but slightly submerged. So these are really things that can happen. We are now also extending the tank measurements. Most of the measurements will be done by FLIS, Flemish Institute for the Sea, and we will be looking at different polymer types, but also looking at samples which are artificially weathered, and where we also introduce some biofouling. We're also doing some more outdoor measurements, looking at gill whitecaps. And from VITO side, we will be implementing or further developing our AI model. So thank you a lot for your attention. I would like to thank also our funding agencies. And I give here the link to our remote sensing marine litter case page, where you can find our publications, but also where you can find the link to the open access database. So thank you.